Our goal as solar cell engineers is to convert as much of the energy in the light incident on the surface of our cell to usable electrical energy. The first step in any road to improvement is identifying the obstacles. We shall therefore truly commence our discussion of optics with an overview of the optical losses in solar cells. There are many solar cell designs for a wider range of application. But whether we are designing high-performance solar cells to power space exploration or thin, flexible solar cells to charge your camping site in the outdoors, all solar cells are subject to the same set of design rules. Optimizing the design of any type of solar cell involves a delicate interplay between three concepts. These are shown in the figure. Spectral utilization aims at using as large a fraction of the incident solar spectrum as possible. Bandgap utilization involves the collection of the generated charge carriers. It therefore considers the electrical losses in solar cell which determine the voltage generated in reference to the bandgap. Finally, given a certain semiconductor absorber, light management focuses on maximizing the absorption of light and subsequent charge carrier generation in the photoactive layer of the solar cell. The bandgap utilization has been discussed earlier in this course. Therefore, in this video, we will focus on the spectral utilization and next on light management. The learning objective for this video is to understand the loss mechanisms that limit the spectral utilization of a solar cell. We will learn how this fundamental limit depends on the absorber material and how to calculate the fraction of solar spectrum that can be utilized. Finally, we will look at the optimal bandgap energy for a single junction solar cell. Any single junction solar cell can only utilize a fraction of the incident energy. To visualize this, we take a look at the band diagram of a semiconductor material. The blue box represents the valence band. The valence band contains the allowed energy of the bound valence electrons in the semiconductor material. The yellow box represents the conduction band, which contains the allowed energy levels of the unbound electrons. The space between the valence and conduction band represents the bandgap. The green line is an incident photon. As we recall, the photovoltaic effect involves the absorption of a photon with an energy that is at least equal to the bandgap energy. This excites a valence electron from its bound state in the valence band to the conduction band. The excitation of an electron leaves a hole in the valence band, denoted by the blue circle. Of course, not all incident photon energies are exactly equal to that of the bandgap. Therefore, depending on the bandgap energy, there are three possible scenarios. The photon energy can be less than, equal to, or greater than the bandgap energy. We have already seen that when the photon energy is equal to the bandgap energy, no energy is lost. Let's now consider photons with energy less than the bandgap energy. These photons do not have enough energy to excite an electron from the valence band to the conduction band. Since there are no allowed energy states in the bandgap, these photons simply pass through the semiconductor material. The semiconductor material is essentially transparent to the photons with an energy lower than its bandgap. We call this a non-absorption loss. If, on the other hand, a photon has an energy greater than the bandgap energy, some of its energy is lost as well. Upon absorption of a photon, the valence electron will be excited high into the conduction band. Shortly after excitation, however, the electron will relax back to the conduction band edge. The excess energy is thereby converted into thermal energy. This thermal energy is in fact a loss, since that energy can no longer be utilized as electrical energy after charge carrier collection. This process is called thermal relaxation or thermalization. To put it simply, if a solar cell absorber has a band gap of 1.1 electron volts and a photon of 1.6 electron volts excites an electron hole pair, then the solar cell can only utilize a maximum of 1.1 electron volts from that photon. 0.5 electron volts of the energy are therefore lost to thermalization. In later videos we will see that this is an upper limit and solar cells actually extract less than that, but this is a good way to understand the losses that occur due to thermalization. From these two effects, non-absorption and thermalization, we can see that there is a trade-off when selecting the band gap of a solar cell. If the band gap is too large, much of the solar spectrum will pass through the solar cell due to non-absorption. If the band gap is too small, the solar cell will indeed absorb a lot of light. Much of the energy of that light, however, will be lost due to thermalization. So, how large exactly are these losses? We can determine that using this equation. It shows the fraction of incident energy that the solar cell can use, indicated by P use, as a function of its band gap energy. Lambda g denotes the photon wavelength that corresponds to the band gap energy of the absorber material of the solar cell. By integrating the spectral photon flux over all absorbed wavelengths and multiplying it by the band gap energy, we find the amount of usable energy. The fraction of usable energy is then determined by dividing with the total amount of incident energy. This figure gives an impression of the usable fraction. The spectral irradiance of the AM1.5 spectrum is illustrated by the yellow area. The red area illustrates the fraction of energy that can be used by a single junction crystalline silicon solar cell. Such a solar cell has a band gap of 1.12 electron volts, which corresponds to a wavelength of roughly 1100 nanometers. Much of the energy in the short wavelength range in reference to the band gap energy is lost due to thermalization. In the long wavelength spectrum, the losses are caused by non-absorption. This figure visualizes the trade-off between using an absorber layer with a large or a small band gap energy. This figure shows the fraction of usable energy as a function of the band gap of the energy of the material. The usable fraction is also known as the ultimate conversion efficiency, since it's the efficiency of the solar cell without absorption or collection losses. Naturally, the usable fraction depends on the irradiance characteristics. Therefore, it differs slightly between AM1.5 spectrum on Earth, the AM0 spectrum in space, and the spectrum of a perfect black body radiator. The trade-off between thermal relaxation and non-absorption defines an optimal band gap energy. As we can see, this optimum is around 1.1 electron volt. Just another reason why silicon, with its band gap of 1.12 electron volt, is of such interest to photovoltaics. Gallium arsenide, having a band gap of 1.4 electron volt, has a high conversion potential as well, as shown in this figure. In later videos, we will show a trick on how to utilize more of the spectrum using so-called multi-junction solar cells. For now, it's good enough just to understand the basic concepts behind spectral mismatch. So in summary, we saw that all solar cells are subject to the same set of design rules, of which spectral utilization is one. We learned about the two main ways that losses can occur due to spectral mismatch. These are the photons with a lower energy than the band gap will not be absorbed at all. Secondly, solar cells will lose some of the energy of the photons higher than the band gap due to thermalization. These two processes put an upper limit on the spectral utilization of any single junction solar cell. Finally, we saw how thermalization and non-absorption define an optical bandgap energy of about 1.1 electron volt. In the next video, we will discuss the last design rule, light management.